Good morning, everyone. How are you all doing?
Great.
Yes?
Good.
Yes, very good. Good to see your smiling faces again. Um, so, are you ready for the next lecture? We're going to dive into the t-test, which you already had last year. But before I'll jump in, I think it might be good to address some of the points you raised last week. Again, feel free during the whole lecture to interrupt me, to ask questions. If you don't have any, if you have earphones and you don't have any noise in your room, you could also turn on your audio so I can hear your reaction. So that always works good in the interaction for me. So one of the points I wanted to raise was the online collaboration, because a few of you raised last week the issue of, well, it being hard to get through the SPSS assignment, and well, being it's online, the assignment, and that raised an issue with me in the sense that the SPSS assignments have always been online only, so we haven't ever provided extra tutorials for going through SPSS. So after some discussion with a few of you, well, we concluded that it's the collaboration part, I think, where you sit down as students together working on the assignment, and you can show each other your laptop and what you are doing, because I totally understand that it's very hard to describe in words what is going wrong on your in your session in SPSS. So being able to share your screen, I think, is something that is very useful. So I've posted an announcement on Canvas describing how you can use Microsoft Teams. I heard that it was tested and by some students, and that it worked. So I would really like to encourage you to sit and work on your assignments together. And if you run into any problems, then share your screen, and maybe you will be able to find out what is going wrong in that way. So I think it's a good idea to just plan these online sessions yourself. So in Teams, you are able to just do it yourself, everything. So I hope that works for you. So it's not only I think it's good to not only do that while working on the assignment, but maybe also looking back on the assignment. So you've already had two. The feedback is now available on those assignments. So I encourage you to go look again to at those assignments to see what went well, and what could have been done better, and also what the answer models are, because those are available. The question is, how can we find the feedback? So if you go to Test Vision, you can go to the assignment through the feedback option, I think. And there's a video on Canvas in each weekly assignment on how to get there. So look into that. So it's a really good strategy to see what you've done wrong and what you should have done, and you can really learn from looking back at your feedback. Is that okay with you guys?
Yeah.
Yeah. Good. So try to maybe well, you've met each other last year, so maybe you have a group of friends already. So try to come together and work on these assignments and look back on that. Okay, we'll see how that goes, and we'll go from there. Okay. So, you ready?
Yeah, ready.
Cool.
Yeah.
So for today, we're looking at the t-test, the t-distribution in particular, and the one sample t-test. So that's a bit of a repeat of last year. The reason we do it is because we in the meantime introduce using R. So we're going in the weekly assignment, we're going to use R to do some calculations, and this will be needed in the rest of the course for being able to calculate test statistics and having a more fundamental understanding of what is going on in the black box of SPSS. And the reason I also added the t-distribution to the list is because I want to relate this, especially the t-distribution, to what we've been talking about in the past few weeks, namely the null hypothesis testing under the Neyman Pearson paradigm. And we're going to look how it's how it looks like how it looks a lot like what we've been doing with the binomial distribution. So we're going into that. Yeah. So again, I feel a bit interrupted again with the chat. Do feel free to post it in the chat, but just turn on your mic. Just ask the question. It's absolutely no problem. Will you? So the question is, do you have to do the t-test in R or in SPSS? You have to be able to do the analysis in SPSS, of course, but you have to be able to calculate the t-test statistics in R. So we use in this course SPSS for essentially being the statistical package for the social sciences, and which are your tools for scientific research. But we use R to view the black box in SPSS. So where SPSS just gives you some t-value, we use R to actually calculate that t-value, so you know where it comes from and what it represents. So we'll be doing both. Okay, I understand that maybe you're not in a place where you could actually ask the question. So if anyone else reads the chat, then feel free to voice the question that is posted in there. Okay, so these are the topics for today. The slides or the handout is already online for you to use in Canvas, so you can take that to follow along if you wish. So the first thing when we are going to this t-test is of course where it came from. It was thought of by Gosset, and Gosset he worked in the Guinness brewery making beer, or well, he didn't actually make beer, but he for everyone that ever worked in a factory, are there people here who've worked in a factory before? I did at one time. I had to push pins in a machine, and then it did something, and then I had to put another one in, and that went on for hours and hours. So I did factory work once. And one of the things with factory work is that you have to be precise. Not the fact that you as a worker, of course, have to be precise, but the machines also have to be precise. And if the machines that you use get off track, then well, the whole production could be lost. So for this kinds of factory work, but also in a brewery, you have to be able to monitor the margins of error that you have in the stuff that you create. So if you have to monitor your production, then what happens normally in a factory is that you take a sample and then determine if the measurements of those sample are within specifications, within the margin of error. And the larger the sample you need to take, the more time and effort it costs to check your production value. So Gosset was tasked with finding out if he could sample smaller sets and have an accurate estimation of the actual measurements in the brewing process. I don't know exactly what he did, but within the brewing process is if everything was on spec. And that's how the Gosset determined how to set up actually being more precise with small sample size. So that's the main focus that he had in his research. And because he worked for a public company, that meant that he had to sign an NDA, a non-disclosure agreement, which some companies still have, of course, in these days and age, which meant that he couldn't publish his findings to the world. So what he did is he published his findings on a pseudonym called Student, hence the Student T-test. And by that name, he actually solidified his work in statistical analysis. So that is where he came from, and the background of Gosset. So what we're going to try to do today is relate the things that the notion of this sampling and sample distributions, and how you get from this notion of a t-test to a sampling distribution, which actually represents the distribution of the t. So you don't have to understand the R code that I'm showing you right now, but I'm going to point out a few things, and if it's not clear, then let me know. Just voice it, and then I'll try to do my best to make it more clear. So we're going to sample 56, let's say, subjects or participants, or if it would be actual research with people, then this N would indicate the amount of people that you would sample from your distribution. So that means that if I take a sample, then what I'm going to do now is do a random sample with a fixed population mean and a fixed population standard deviation, which is called sigma, and mu is the population mean. And any idea what this kind of population that I'll be sampling represents? Looking at these two.
IQ.
IQ, indeed. So I'm sampling. I'm specifying a population mean of 100, and the standard deviation for IQ is 15. So it's indeed IQ. And if you looked, then you would have seen the IQ standing right here. So we're going to do sample a few. So in the next slide, what we'll have here is the theoretical population distribution of intelligence with a mean of 100 and a standard deviation of 15. And I'm going to take a few samples. So this top left is just one sample from this distribution of 56 observation. So it's just a random selection of this sample. Is that clear? I'm not going to do one, but I'm going to do a lot. So what this represents is actually the same as we've been doing with the binomial distribution, is where we said, well, we know what the population parameters are. For the binomial distribution, it was the binomial distribution, well, throwing 10 times, where we assumed the population to be, the coin to be fair. And we had one sample, but our sample distribution for the binomial would indicate the numbers of heads versus the numbers of tails. Whereas if you have a continuous variable where you just sample random values from this population, then you could, with a sample of 56, you could have any value there. So what you see here is that within this sample, if you plot this distribution, you get these, well, sort of normally looking-ish results. But this is just one sample. And what I did is we actually have a lot of samples from these. So where I'm going at is that I actually want to do the same thing as the thing we did with the binomial distribution. Is I just want to take a lot of samples from this known distribution and determine in essence what the sampling distribution is from based on this population distribution. So we'll be doing this, and one thing that we have to think about is that we have to go at one point from taking a sample, calculating a mean within the sample, to going to the test statistic. So for the binomial distribution, our sample would be thrown 10 times, and it was quite easy to go to the test statistic because we defined our test statistic as being the number of heads that we've thrown. But with a t-test, you have to go from your sample and the information that you have from your sample, namely the mean and the standard deviation, to a t-value. And this is what the thing that Gosset actually contributed to the field is that he thought, well, instead of calculating a standard score, a z-score, by dividing the sample mean subtracted with the population mean by the standard deviation, he said, well, no, let's divide it by the standard error, because the standard error takes, well, the amount of error that you have in your sample, where the sample size actually plays a role into consideration. So if you do that, then you end up with a t-value, and the t-value here is defined for a specific amount of degrees of freedoms, which is in this for the t-test n-1. But if we look at this, what actually is going on, then we see that we actually have the sample mean, that we subtract the mu, so the thing that you would the value of the population that you think would be the case. We'll come back to that later. And you divide it by the standard error, where the standard error, of course, is determined by the standard deviation of your sample, this one, and is divided by the square root of n, which is essentially the definition of the standard error. So this is the t-test, but we'll get there. So let's first look at our sample. So if I just take one sample from this population distribution, then what I do here is I use the function rnorm, which is a random normal, and I sample n, the number, which is 56, with a specified mu and a specified sigma, and what that results in is 56 numbers, which are actually random samples from this normal distribution. Does that make sense?
Yes.
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 Is there anything that you find if you look at these numbers, is there anything that stands out in particular?
They're like numbers with a lot of decimals.
Exactly. There are certainly a lot of decimals. And what can you say about these numbers with a lot of decimals?
That they're all around 100.
That because you sampled from a normal distribution, that they all vary from this population mu of 100, indeed. I see in the chat that someone says, well, it's continuous. And why would you say that it's continuous? Anyone else can...
Because the numbers can take on any value.
Exactly. We can have any value on the spectrum. So that makes the fundamental difference, and we're going to see that when we actually calculate the t-value. That makes the fundamental difference between what we've been looking at last week, where we had a discrete distribution where you could only have exact integers, to going to a continuous distribution where you have every possibility to have every number in between. So that's exactly the case, and what we also see is that we don't have any number that is the same in this random sample. It differs for each and every number that we have in here. So if we would plot the population of the sample distribution, that would mean we make a histogram only of this sample. So we're going to do that, and this is one of those histograms that I've shown in the earlier plot. This is just one of them, which has a mean of 99.42. And this is the spread that we have within here.
Can I ask a question?
Of course.
Why are we using a histogram? Because it's like a continuous variable. Do we just fit like everything that's between 90 and 100 in this bar of that's high there?
Yeah, so the difference between a bar plot and a histogram is that a bar plot represents bars with the discrete values, and what a histogram does is that it actually bins all the values that you actually have between set bin sizes. So we have a bin size here from 60 to 70, so all the numbers that we have here, which are between 60 and 70, fall within this bin.
Okay.
Yeah?
Yeah.
Very good. So what we want to do, yeah?
Is the t-test only for continuous variables?
You use the t-test in itself is a continuous variable. Is continuous. The t-value in itself is continuous, which if you follow the test selection scheme in field, you would end up with a t-test if you start out with the dependent variable, the thing that you actually want to measure, being continuous. So yes.
Okay, thank you.
So the independent variable doesn't have to be continuous.
Could you repeat that?
So you said the dependent variable needs to be continuous to use a t-test. Is that correct?
Yeah.
But the independent variable doesn't need to be continuous.
No.
It can be categorical. But
yeah.
Okay.
And we'll get to that, and we'll have more examples of this in this lecture, but in the next lecture we'll look into two specific t-tests. Okay. So what we want to do now is do the same thing that we actually did in the previous lecture, and that is go from a sample and a sample mean to the test statistic. So if we want to determine what the actual t-value is for this specific sample based on this mean and based on the standard deviation, we apply the calculation of the t-statistic, which is actually straightforward, where we specify what our sample is, and we subtract that by mu. What is mu again?
100.
Yeah. So what are we testing with this t-test?
The difference between the sample mean and the population mean.
Exactly. Very good. So to do that, we have to divide by the standard error, and the standard error is defined by the standard deviation of x, where x is actually the vector of all the values that we had. So x is it's not the mean of x. It's not with the bar on top of it. It's just x, and x represents all these numbers that we have here. So this x, there are 56 numbers in there. So we calculate our t-statistic based on our one sample. Makes sense still?
Yes, still makes sense.
Cool. So now, what would happen if we would do that a lot more times, where we actually know what the population parameter is? We sample from this population parameter, which all have set population means of 100 and set population standard deviation sigma of 15. What if I don't just have one sample, but what if I have 1,000 samples? So this is what I do here. We have a loop, and we loop through the thing we did earlier. Well, we're going to take one random normal sample with specified n of 56, with a specified mu and a specified sigma, and we're gonna run that 1,000 times. And what we want to do then is apply the same as we did before, where we said, well, we now have 1,000, and I only showed you the first 6, but these are actually 1,000. They just keep going, where for each and every sample from the same population mean with the same standard deviation of the population, we have the actual sample mean, and we have the actual where we calculated the standard error of this mean based on the standard deviation, of course. So that means that I could actually calculate the t-value for each and every sample that we took here. And if I do that, I can create the sampling distribution of the t-value. But to have a notion on the fact that you could create a sampling distribution also just based on the means, you could also say, well, what are all our means, and what does that look like? So this is a sampling distribution, but it's not based on our test statistic. It's just based on all sample means. Is that clear?
Not completely.
Yeah. So what we're doing now in this same histogram is where we just say, well, we have 1,000 means, 1,000 samples, just like every one of you threw a number of heads last time, but we were not with 1,000 students. But if we would have had 1,000 students, we could replicate this experiment based on set parameters, set mu, set and set sigma, and we could create this sampling distribution of the means, which would show on average, with the highest frequency, a mean of 100, and then it would fade out to the sides. But we're not looking at just the means. We want our test statistics to be the t-test statistics. Why? Because we want to take the sample size into consideration, and not just the sample size, but more the lack of measurement precision, so the standard error in essence of a small sample size into consideration. So instead of just using the sample means, we could calculate for all 1,000 observations, for all 1,000 samples that we took, we could calculate the t-value. So this would be for this first one. These are the last 5, 6. where we have our sample mean, which is 102 and something. We have our mu, and we have the standard error of this sample, and applying the t formula will yield us a t-value of 1.5688. If you do this, what would you think the expected value for the t-statistic would be?
0?
Exactly, 0. Because you would assume that if it was a random sample from this population with specified mu, which is 100, the difference on average between the actual sample mean and the population mean, which you specify, would not exist, would be small. So it would be 0, indeed.
Excuse me, do we have to know how to do this on R for the exam?
No, you don't know. You don't need to know how to do these sampling distributions. You don't need to know how to do a loop to create all of these. You do need to know how to apply the t calculation. So I could give you a sample mean and a standard deviation, and I could ask you, well, what is the t value for this specific sample?
Okay, thank you.
We don't have to make a t-value distribution.
No, you don't. And I'll show you why in a few minutes. Because if you have all these t-values, you could actually create a sampling distribution based on all these t-values. So instead of using the means of all these samples, we could just use the t-values for all these samples. And this is what I'll show you here. So exactly as you pointed out, our expected value for t is 0, but we also see that our standard deviations are set to be increments of 1. -1, -2, -3. It fades out at the 4s. But what you also see is that I've added a line. And this is the same underlying trick, of course, that we applied with the binomial distribution. At one point, I told you, well, it actually is quite insane to replicate so many times to get a notion of what the binomial distribution looks like, because we can actually calculate the binomial distribution. And this same holds, of course, for the t-value. You can calculate the t-distribution, and you don't need all these samples. But I wanted to go through the same steps to cement the notion of a sample going to a sampling distribution, applying that to the test statistics, and what you end up with is this probability distribution, which is in essence t-distributed. But we can calculate it off the bat. And that means that if you just apply the t-distribution, the probability density function for the t-value, you can just create such an exact curve on all the continuous probability space for the t-statistic. Also, you don't have to be able to apply this function, but it's for your conceptual understanding of what is going on behind the scenes when we're talking about a t-distribution. Now, one of the things is that within the t formula, let's go back here, there are actually three pieces of information that come from your data. First, it's the sample mean. Second, it's the standard deviation within your sample. And third, it's your sample size. And the sample size has quite a large impact. So that actually means that if I would have different sample sizes, my t-distribution wouldn't look like this. Do you have any idea what this would look like for different sample sizes? What would be the effect of sample size on this distribution?
Wider.
wider. Who agrees with you?
I do.
Who doesn't agree?
What was the question again? Sorry.
The question is, if you would have different sample sizes, what would happen to this distribution? And one of the remarks made is that it might be wider.
Wider when what?
Wider when the sample is smaller.
So if the sample, you think that if the sample is smaller, the distribution would be wider
Because of more error.
because of more error. Who agrees?
I think
Yeah,
if you assume that your sample is a good all your samples will be a good representation of your population, it shouldn't change that much, right? So it should be approximately still the same then.
So assuming that your sample would be a good approximation of your population, it would more or less stay the same.
Yeah.
Anyone else? Different thoughts on this?
Because the t-value is calculated by dividing through the sample size, I guess if the sample size gets smaller, the t-values get larger? Or the chances of getting a higher t-value increase?
That's yeah. You're going absolutely in the good direction. So, but what effect does it have then on this distribution? So one of the remarks was it would be wider. So instead of having going from 0 to 1 to 2 to 3 and stopping there, it might go spread to 8 or something.
It flattens the curve?
It
Flattens the curve?
It flattens the curve. When will it flatten the curve? When the sample size goes up or when the sample size goes down?
When the sample size goes down.
Is there anyone who disagrees that the curve will flatten if the sample size goes down?
I thought maybe just the whole distribution kind of shifts to the right.
No,
because the t-values.
No, the distribution doesn't shift because you always subtract your found test statistic. Your found sample mean. You subtract the population mean from that. So it will stay centered on 0.
Okay.
So, but we're stuck on the flatness of the curve.
But I think then still the more samples you will add, the steeper it will get, because you will approximate more to the 0, because you assume that your sample means and your population means will be approximately the same. So when you have less samples, it will flatten.
Okay.
No?
Is there anyone who doesn't agree? Now's the time to speak up.
I think the curve, it flattens whenever there's more samples.
Yeah. Why? Why do you think that?
Well, I think that because it just makes it more normally distributed whenever there's more samples, then I'm not sure how to explain it.
Yeah, you're going in a good direction. Yeah.
I think the more samples there are that have a t-value of 0, because the difference between the population mean and the sample means, there's more of them that have where the difference is 0.
That could very well be, but the question is, how does it relate to the tails of the distribution? Because what was stated here, and I won't push on any longer, but if your sample size increases, the tails will get flatter. And as was mentioned, when you increase your sample size, it approaches actually a standard normal distribution. So that is actually what is happening with the t-test. if you calculate a t-distribution like we have here, the higher the sample size, the more the distribution that you will have, this curve, will be the same as a standard normal distribution. But if your sample size is smaller, and that was the thing that Gosset added to his precision of measurement, the tails will actually increase. So what I've shown here is different t-distributions with different sample sizes. And what you see here, for example, is that with using a small sample size, a sample size of 5, so if I would have had this whole resampling, if we wouldn't have applied it to 56 sample size, but just 5, and I would have done that 1,000 times, and I would have looked at that distribution, then we would have so-called fatter tails. So we would have more observations of extreme values within this distribution, which actually makes sense, right? If you have a population distribution and you only sample 5 people out of that, then that could be a fluke. You could have only 5 from the top. But if you increase your sample size, if it's actually a random sample, then it could be more all over the place, and it would be not that likely that you sample only from a very, very high values. So the tails increase if the sample size decreases. Does that make sense?
Yes.
Yes.
Okay. One of you also mentioned that maybe with the variation of the sample size, we actually see a wider or a tighter curve, and that is not what we are seeing within the t-test, because we are actually well, it's a standardization method, of course, because we divide by the standard deviation, and we use actually the square root of n to actually divide by the standard error. So it all stays put, centered between 0 in standard deviation steps of 1, but based on the sample size, it's either flat, it's either fatter at the tails, or it's narrower at the tails. And well, you could argue that if you have a sample size of 5, then this would fade out to infinity a bit further. That's true, but if you look at this graph, well, if you have variation in sample size between 5 and 100, where 100 approaches a normal, standard normal distribution, the values of the t values are always between -4 and 4. So that's about the range. And this is good to take note of, because if you find a t value based on a sample, for example, if you wouldn't have any notion on how to calculate a t value and how to calculate a p value, if I would ask you if a t value of 1, if that would be significant, what would you say?
It's no.
You say it's not significant? Who agrees?
I agree.
Yeah. So this is quite intuitive, right? You see what is most frequent. 0 is most frequent. 1 is also very frequent, but getting a value of 4, well, that's not very frequent. But there's no debate on if you find a t value of 1 if that is significant or not. It's just plain not, because it happens very often if the assumption of the null holds. Does that make sense to you?
Yes.
Yes.
Okay, very good. So in terms of hypothesis, where we actually, for the null, of course, our hypothesis is that we don't find any difference in our sample between our sample mean and the population mean. Our alternative hypothesis could be, well, then the sample mean is not equal to the population mean that we have for two-sided tests, so it can go both ways. But for the alternative distribution, for the one-sided test, you could actually define a direction. So maybe your hypothesis is that that females are more intelligent than the general population. Could be. Then you could test this. You know what the population mean is. It's 100, so you could have the hypothesis, the one-sided hypothesis that our sample mean, the mean of the females, are higher than the population mean. Or it could be the other way around. So applying that notion to determining the amount of error that you allow yourself, or in other words, the type 1 error that you allow yourself to make, means that you would have to divide your type 1 error either by both the sides that you have, or just put everything on one side. So what was the type 1 error rate that we allow ourselves to make mostly?
5%.
Exactly. And we have to realize again that this is a choice. But indeed, it's 5%. So if you would test two-sided, then your alpha area would have to be divided on both sides. So I've got a question for you, and this is something that you might get on an exam. What actually is on the x-axis if you look at this graph?
The amount of standard errors that our sample is away from the mu.
The the y-axis. Did I say x?
Yeah, you did.
I did. Oh no. So the x-axis is actually quite simple because it's just a t-value. If you see that I have given it a label, it can be a t-value of 0 or 1 or 2 or 4 or whatever, but it's the t-value on the x-axis. Okay, now the hard question. What is on the y-axis?
The relative frequency of finding that t-value?
I hear the frequency of finding that t-value.
The probability of the t-value.
I hear the probability of the t-value.
Proportion.
The proportion?
The probability of finding a sample with that t-value in the population.
The probability of finding that t-value in the population. Anything else?
The proportion of different samples within. So if we get a sampling distribution and then we calculate a t-distribution, there are multiple samples. So the y-axis would be the proportion of the samples, different samples that belong, for example, at the center or at the right or at the left.
So this is a very logical assumption to make, because we went through the sampling distribution, and with the bars you could actually see that that the height represents a frequency, and we went from going from bars, the height of the bars in our sampling distribution, to actually defining the t-distribution in terms of a probability density function. So this continuous curve that you see, and this means that we make a jump. We make a mathematical jump from a discrete probability space to a continuous probability space, which actually means that in such a distribution, a continuous distribution, the probability of getting a specific single value on the x-axis, the t-value for in this case, a very specific t-value, the probability is defined by 0. And that's completely unintuitive, because if you look at this graph and you would say, well, if I have a t-value of -2, what is the probability of getting -2? Well, it mathematically is defined as being 0. And you would say, well, this is strange, because if I just look at -2 and I go up, then, well, I see a height here. So this is... What's going on here? Anyone?
Is it because they assume that the only probability should be 0?
No, it's not that they assume that the only probability that is possible would be 0.
Is it maybe the chance of getting that probably like every t-statistic of that value and below?
Now you're getting somewhere. So, elaborate.
So, like 1 point, again, the chance of getting like a continuous t-statistic is 0, but like the chance of getting that t-statistic or every t-statistic below is that chance on the y-axis.
It's very good thought process. So what does that imply? What does it imply in terms of, if you look at these graphs, what the probability actually is? If you have to point to the probability in this graph, what would you point at?
Is the area on the core?
Exactly. So the probability is defined in a continuous distribution like the t-value as the area under the curve. So I've plotted this red area, and that is the probability. So the probability is not defined by the height, but the probability is defined by the area.
But what does the height mean then? What is the 0.4?
That's a good, and the height, if you plot these graphs, the label for the y-axis would be the probability density, the density of the distribution. And the density is not really informative, because we actually want to know what the probability is. So probability is defined by an area, and you have to determine what the area under the curve is where you are willing to make a mistake. So in terms of our allowed chosen type 1 error, if we choose 5%, we're talking about an area under this curve. So here I have 5%, and it's all on the right side here. Where if I would have chosen to test two-sided, my alpha would be 2.5% on this side and 2.5% on that side. Does that make sense?
Yeah. But I still don't fully get what information does the density give us. Is it how frequent the t-values are?
No, it's how, well, it's essentially most accurately described as how dense is this distribution.
Mm-hmm.
So it doesn't specify frequency; it specifies density, and this is a hard topic to grasp if you're not very much into the mathematics of this, and you don't have to be for this course, but you do have to understand that when we're talking about probabilities in continuous distribution, you're talking about areas under the curve. And this curve we've seen, this curve can vary. Because if I have a small sample size, the curve is different. It's fatter in the tails than if I have a large sample size. Then it's shallower at the tails. So that means even if I have 5% as my criterion, depending on the sample size, this 5% would either be more to the right or more to the left in the tails, because the distribution can vary. When I go from this type 1 error, let's for example say that we choose to test two-sided. With what values of my sample would I reject the null? So I take a sample, I get a sample mean, I use the sample mean and the standard deviation and the sample size to calculate a t statistic, a test statistic. At what values of that t value would I reject the null?
Would it be a one-sided or two-sided test?
Let's assume two-sided. So this one.
So everything above 2 point something, or below minus 2 point something.
Does everybody agree?
Yep.
Yes.
Yeah.
Very good.
Yes.
And if that is the case, so for example, if I had a t value of 3, which obviously is at the outskirts of our criterion, it would be totally obvious that this is rare. It's a rare t value. And what would be the probability of finding this t or more extreme?
7 years.
In terms of area.
It would be probably 2 times the area that's between the point that you get and the extreme values, more extreme values. So the area between the point and everything that's to the right from this, and because it's two-sided test, you would calculate times 2.
Exactly. So it's the area from the t statistic that I found in my sample going to actually infinity, but it's under the curve, right? Under this specific curve, so under the assumption that the null hypothesis is true, it would be the area from that t statistic to the extremes. That would be the probability of getting that t statistic or more extreme. And because we're actually testing two-sided, you would also have to do that on the other side. So that's absolutely true. And how do we call this probability?
P?
The p-value, exactly. Oh, we're getting there. Very good.
Can I ask one more question on this?
Of course.
So you said the probability of finding an exact t-value is 0, is that correct? But then the probability of that value and more extreme, that's actually the p-value.
Yeah. Exactly.
So then what is the reason that the probability of finding that exact t-value is 0 because there's basically an infinite amount of t's that you can find?
Yeah, exactly.
Okay.
So you could find t point 4, 3, 5, 6, 5, 1, 6, 5, 6, 7, 8, or something else, because it's a continuous distribution. Each and every possible outcome is comprised of the probability space, where if you think about that and you add one digit, then you could even have one between that. So it's a matter of definition of the continuous probability distribution, that the probability of a specific value is defined to be 0. Okay. Now we go from t-value to effect size. So when you have a t-value, I told you earlier that it's actually not enough to just refute the null hypothesis, because we, as you've seen, if you increase the sample size, you will find some significant difference at one point eventually. So to get a bit more understanding of what the effect size is, you can transform the t statistic that you have found in your sample to an effect size r, which is not the correlation, but so it's just an effect size measure. By applying this formula, you'll be doing this at some points in this course. SPSS will also provide some effect size measures, and these effect size measures are again based on your data, because you don't actually know what the alternative distribution is, right? Just like when we didn't know that what the exact alternative distribution of the binomial was of the coin that I had from Conrad, if it was the probability of 0.2, if that was correct or not, I didn't know. So it's based on your data. And our effect sizes that we calculate, so this specific effect size of R, you could also think about that, what under the assumption of the null being true, what would be a rare effect size? So you could make the step, and that is actually what Cohen did, to have a notion on the effect size, to look at, if you assume the null, as I've done here, we can calculate actually the effect size, and that's what I've done here. I don't know if you can see this. Yeah, here it is. So I use the t-value and the sample size, or the degrees of freedom in that matter, to calculate for each of our 1,000 samples the effect size. So I find an effect size of 0.2, and I find an effect size of 0.04, etc., etc. So I now have a vector of 1,000 effect sizes based on the assumption that the null is true and that there's absolutely no effect. So if I were to plot this vector of all possible effect sizes under the assumption that the null is true, that would look like this, where values between 0 and 1/2 are most frequent, and it fades out. It becomes less frequent within under the assumption that the null is true when you get to about 0.4. And Cohen in 1988 gave some benchmarks on how to interpret your effect size measure. So he divided it into 3 sets: small, medium, and large, and said that and defined the ranges of those effect size. And you can, of course, if you look at this plot, you can deduce, of course, that it's quite obvious to have it within these ranges, because it's a small effect size. It happens a lot when under your assumption of the null. So this is where that comes from. I want to look at the power and combining the null and an alternative distribution. But I think my brain is about fried right now, so I absolutely need something to drink. We'll be continuing at 15 past 2. Is that okay with you?
Yep.
Cool.
Yeah.
We're gonna get something to drink.
Yeah.
Okay, we will be continuing. I have my coffee, so I'm ready to go. So we've looked at effect size, and we discussed earlier that within the Neyman-Pearson paradigm, we actually need to specify in advance the errors that you allow yourself to make, in the sense that we define our type 1 error, our alpha to be 5%, so we want to be wrong 5% of the time in the long run. But we also need to think about the beta, or to put it more correctly, about the power that we would have in a test, 1 minus beta. So the probability of making a good decision. So if some alternative distribution would be true, if I would reject the null, what would be the probability of that being a good choice? So we already discussed that we would strive for this power to be about 80%. But then we have to think, and we've talked about this last week. We have to think, how do we get a notion of what this power could be, and this is based on the effect size. So when replicating studies, or when doing research for new studies, you can find out what the effect size of previous studies are, and you can use that effect size to determine what actually the sample size needs to be to get a power of 80%. So one of the standalone applications that you can use for that is G-Power. You can have a look at that at one point. But what G-Power essentially does is you specify that you want to make a type 1 error of 5%. You specify the percentage of power that you want to have. And you specify what in previous research the effect size has been. And based on that, it will produce the sample size that you will need to have for your research. And only when you use that approach, you will actually have a grip on the type 1 error and on the actual power that you will like to strive to have. And if you deviate from those sample sizes, then you will your grip on the amount of mistakes that you would make in the long run would diminish in effect. So that means, and it's related to this different point, that you have to specify then in advance, based on findings of effect size of previous studies and your alpha and your power, what the sample size is. And especially for psychological research, and also at our department, if you do research at our department, then you have to go through the ethical committee, and one of the things that you also have to provide is the results of this G-Power analysis, which actually tells you how many subjects you should use for your research. Doing this ensures that you don't p-hack your way to significant results. So you have the grip, you have to specify this in advance, and we use G-Power to calculate this. But to get a bit more of a notion and to relate what we've talked about last week with the binomial distribution in terms of power, we're going to do the same here with the T statistic. So we've seen that for some number for some sample size, we could determine what the T distribution would look like. We know that the sample size determines the fatness of the tails. in a sense. But we could also specify some alternative distribution. So what I've shown you here is what the alternative distribution for t value could be. So again, what I'm showing you here is hypothetical. So let's imagine that there, for some subsample of your population, there actually is an effect. There actually is a difference between the population mean and these sample means, or to put it more specific, that the sampling distribution of this specific subset within your population is this mu, this population mean of this alternative distribution, would be in terms of t-value would have a t-value of 2. So this is what I plotted here. So we have the null distribution for your t-value, and I've plotted the alternative distribution. That's this blue one. Both have a population mean, being of course 0 for the null assumption, and in this specific case being 2 for the alternative assumption. So this is completely analogous on the binomial distribution that I showed you last week, where you can determine what the type 2 error is that you are willing to make. Where do we see actually this type 2 error? And
sorry, could you repeat the question?
Let's rephrase it. Where would you see, if I would ask you, point me to the type 1 error? Where is it?
See it at the alpha level?
Sorry?
You can see it at the alpha level?
You can see it at the alpha level. And let's assume that we have chosen an alpha of 5%. So looking at an area under the curve, which one is it then?
The
left of the critical t-value.
I hear the left critical t-value.
Underneath the red.
So it's underneath the red curve, exactly. So your assumption is that the null distribution is true. Your 5% is the area, because it's a probability, right? The 5% relates to the probability of making this mistake, is 5%. So it's an area under the curve. And the fact that your critical value lies here is because the area, if you want to have 5%, then your critical value stops here. That makes sense, right?
Yes, but just one question on this. The 95% you can calculate by having 2 standard deviations from the mean, right? That's in general the average.
Yeah, that's a general thing, but that's based on the standard normal distribution, right? And this is not a standard normal distribution. This is a t distribution which has feather tails based on the sample size.
Okay. Sorry, I thought for any normal distributed thing that would count, but that's not the case.
Yeah, that's not the case indeed.
Okay.
So you actually have to calculate what is the exact critical value based on this 5%. And you could also imagine that if you would have a larger sample size and these tails would have been less high, then our 5% would shift to the left, for example. So that's right. So we find our type 1 error we find under the red curve up until the critical value. So it's this area, and it goes actually to infinity and back, and then here we have it. So where do we find our type 2 error?
So the type 2 should be also under the alternative hypothesis and to the other side of the power. So from the critical value to the left.
So you're saying that we find our type 2 error under the red curve?
No, under the blue one.
Under the blue one.
Yes.
And starting from where?
From the critical value to the left, to the negative.
Yes, that's absolutely correct. Because our type 2 error was when you assume the alternative distribution to be true and you do not reject the null, what is the probability of that error? So, and also this is intuitively obvious, right? So if you decide not to reject the H0 because your found test statistic lies at the left side, but this blue one is actually true, well, then in all these cases, that would be a mistake. Okay, this is going good. If you look at this plot again, where do you find the p-value?
It's the area under the curve.
The p-value, you're saying the p-value is the area under the curve? Which curve?
Depending which p-value you're, like usually under the red curve, and the area to the right from the t-value would be our p-value, I think.
Anyone disagrees? Different thoughts on this?
Isn't it everything to the right of the critical value on the alternative hypothesis?
Isn't it everything on the right of the alternative hypothesis?
Right, of the critical t-value. So the bit that's been colored in, isn't that the p?
This area?
No, on the whole blue one.
Oh, the whole blue one.
Yeah,
okay.
I think so. Isn't that it?
Who agrees? Who does not agree?
I do not agree.
So I heard someone say I don't agree, and I heard why. Why don't you agree?
So I think it's the area under the null hypothesis, and from your test statistic, like the values that are more extreme than your test statistic. Not under the blue one, but under the red one.
Under the red one. So you're saying it's under the red one?
Yeah.
And I heard someone else say, well, it's not the area under the alternative hypothesis, starting from the critical value, because that is actually the power, and that is correct. So it's a bit of a trick question, because I'm not showing you a p-value in here. I'm only showing you what the null distribution would be. I'm only showing you what the alternative distribution would be. We have determined, based on an alpha level of 5%, what the critical value would be, but there's no p-value in here. So the thing that one of you correctly realized is that at least your probability, your p-value of finding this test statistic or more extreme would lie under the null distribution. And that's correct, because we are looking at the null distribution where we assume nothing to be going on, and what are we comparing the p-value to?
To alpha.
To alpha, and alpha is the type 1 error. So we're determining, based on the type 1 error that we are willing to make, if we either reject the null or don't reject the null. So it absolutely, the p-value is absolutely under the null distribution, under the red one in this case. And you can't see it here because I haven't shown the actual data that we would find. This is just the distributions, the null distribution, the alternative distribution, assuming this alternative to be true, actually true.
Wouldn't the p-value be on the right, under the red curve, obviously, but on the right, starting with the mu, the alternative mu? Wouldn't that be?
So the question here is, wouldn't the p-value be for in this case, wouldn't the p-value be starting at 2 under the mu of the alternative distribution? Why would you assume that? Could you elaborate?
I assume that because I assume that we have this hypothetical alternative distribution based on the sample we have, based on our observations, and we compare our observations to the null hypothesis, to the null distribution.
Okay. So is there anyone who agrees with this?
I would agree. I mean, like, if the alternative hypothesis is based on the sample, the mu should be the same as
okay.
Yeah, p.
Okay. So this is a very good thought process here where you're going to, and you're making a specific distinction, and it's good to realize that if that was the case, how would we call the area starting from the critical value under the alternative distribution? How would we call that?
That's a type 2 error.
That's not a type 2 error.
The area to the left of the critical value?
To the right. To the right.
To the right. Oh, to the right.
So I'm sorry. I will show you. So this starting from the critical value to the right, this area. If that were the case, what you were saying, what would we call this area? What would we call this probability?
That's the power. Would it change under?
You're calling it the power. Who agrees? Try to think back of what we talked about last week. So we addressed this issue on power versus something else. You remember? I'm also eyeballing the chat. So last week we talked about the fact that we don't actually know what the actual alternative distribution would be, right? And that we could guess, that we could assume the alternative distribution to be this, based on the test statistic. And we also concluded that that would be a bit of a problem because, well, it's a random sample. So why would you assume this random sample, the mu of the alternative distribution, to be equal to the actual test statistic that you have found? We said, well, it is a random sample, but if you repeat that a lot of times, then you can do meta-analysis, and then you could determine what the actual population parameter of the alternative distribution could be. And I also told you that SPSS, when it reports power in that way. But it was a special kind of power. It was not normal power.
Oh, do you mean the post hoc power?
Exactly. That's exactly what I'm getting at. So the post hoc power, you define the power based on the found test statistics. So if that were the case, if you would say, well, actually this 2 is my assumed alternative distribution, then this wouldn't be called the power, but it would be called the post hoc power, because it's just based on your specific sample. And so it's so again, the actual power is based on what is actually, well, let's say what is actually real, the real alternative distribution, which of course we don't know, to be clear, but that's what we call power. And if we are talking about the type 1 error rate, type 2 error rate, and power in the Neyman Pearson paradigm, we try to define it in terms of what the actual alternative distribution would be. Of course, based on our best guess. But it's fundamentally different than the post hoc power, because, as you correctly stated, the post hoc power is based on the assumption that your found test statistic is actually the population mean of the alternative distribution. If that were the case, then your p-value would be under the red curve, starting from the blue line. But assuming that this alternative distribution is actually the real alternative distribution and not based on the on your found test statistic, then there is no p-value to be found in here, and the p-value would be the results of your experiment, and then you would see, well, what p-value would I find? So maybe you find a p-value of 2.5, then your t-value, your t-value that you would find would be 2.5, then it would start here, and then you would determine what the area under this curve is, going to infinity and back again, starting at 2.5. That would be your p-value. So, going in that same line of thought, if you would find a t-value in your data of 4, what would be where would you define your what would happen to the alternative distribution as you look at this, and you would view it in terms of post hoc power and based on your data?
Would you center it at 4?
Yeah, then it would shift to 4, but it's still assuming then that it's post hoc power, that it's based on the data that you have found. So that's a good distinction to think of, and it's a hard one to make, because it's very hard to think of some reality that we can't actually observe and being underlying assumption. So it's good to have that clear, but you do have to keep in mind that when you talk about power, you're talking about the actual reality, which is of course very hard to know, because actually we don't. And the next best thing that we do is then, well, I will assume for the post hoc power to the population mean to be equal to the mu of the alternative distribution.
Thank you.
Okay. That's a hard one, right?
Now it's clear. Thank you.
Okay. So I showed you last week that you could look at the site of the ARP psychologist, and what you can do here, for example, if you solve for power, you here see two distributions, the null distribution and an alternative distribution, and you can see that what happens if you vary the effect size. So if you would have a lower effect size, so actually if your Cohen's d would be 0.31, then you can see in this graph, and I would actually encourage you to play with this to see what happens if you increase your alpha, to get a notion of where do we find alpha, where do we find power, and more importantly, what happens when you increase the sample size and everything else stays the same. So this would solidify the notion, or at least make it clear to you that if there's a small effect size and you want to find it, increasing the sample size will actually also increase the power that you have. And you see that happening right here. The light blue area is actually increasing as I increase the sample size. Where if my sample size is too small, I'm not even able to find a significant result. So I'll encourage you to just try to play with this to find out how this works and everything. Okay. Oh, now I closed it. Okay. Good. Here we go. Yes. And we're back. So that's the t-distribution. What I want to do now is look at you at the with you at the one sample t-test, and for this I had planned that you would have to look at the, because I do this always in the lecture hall, and I ask people to look each other in the eye and make the best estimation of the intelligence of the person next to you. So in Zoom, the Zoom variant of this one would be to look at your Zoom screen and the person next to you in your Zoom screen, and look into the pixelated eyes of that person, and then fill in this form and make an estimation of the intelligence of the person sitting next to you. But due to the constraint of time, I won't actually do this. You can click on it, of course, and fill it in if you want to anyway. But my question after that would always be, what is the best estimation that you could give? So what would your estimation be of the intelligence of the person next to you?
100.
100? Who agrees? Someone that does not agree?
I'd say like around 110.
110.
Maybe because we're all university students, so we're but a bit above average.
Yeah, you're absolutely university students, which means that you're above average, but you're higher than 10 intelligence points above average. You're actually 20 intelligence points above average. So what would you estimate the? So this 120 then would be your best guess, right? Is there anyone who would guess differently? I see in the video also that there are two students sitting together. So if they look in each other's eyes, would you estimate? Yeah, I'm looking at you, Edneed. Would you estimate your co-students to be 120 or something else?
Yeah.
How about that?
120 or something else?
160 for him, 100%. 160.
Why?
Oh, I was like, I don't actually know. I was gonna say 120.
So can you think of a reason, and also for anyone else, why you would not opt for 120? Why you would opt for something else?
Maybe because you know them better?
Exactly. And maybe because you know them better means that you know some attribute, maybe study results or some other attributes where you can determine, well, based on that knowledge, you would assume a higher or maybe a lower intelligence for that matter, but there would be an extra variable. So the thing that I'm getting at is that you can determine your estimation quite conservatively on a model that you have for your estimation, which in the most simple case, which we are looking at now, the one sample t-test, you would just estimate the mean that we find in a sample and compare it to the sample mean. or the population mean, sorry. But if you would like to expand this model with more variables, you would be drifting away from these simple kinds of tests and trying to add explanatory variables to build a more complex model to say something about your estimations. And that is, well, if you read field, it's everywhere. It's always about the outcome is determined by the model and the error that you have. And these models can be simple. It can be just a simple estimation of an average, or you could expand on that and having more elaborate models with multiple predictors, or even adding interaction terms to your predictors to try to have a better explanatory model for the outcome that you're trying to find, where the goal is to minimize the amount of error that you have. And with the one sample t-test, because we've not done this now, but if we would have, I would have collected your data based on this form and rerun this presentation. But based on the results of last year, we had found an average of 122.32 with a standard deviation of 7.6. That would be the estimation of the intelligence of the person next to you. So most students, most of you would indeed estimate the intelligence of the person next to you to be somewhere around 120. And then the one sample t-test would test this mean against the population mean for this sample. And we know the population mean for this sample to be 120. So testing this assumption, testing this hypothesis, where the null would be that there won't be a significant difference between 122 and 120. And the alternative distribution would be that there would be a difference if you had two-sided testing, or you specify a specific direction. Would you have any assumption on the direction for this hypothesis? What would you think?
It would be right-sided, right?
Yeah. So what is your assumption with that? Why would you choose for that?
Because the average is higher than normal.
Yeah, the average is indeed higher than normal. So, but if you say that the average university student is 120, then that's the average. It's right in the middle, and it would be skewed. So the rest would be on both sides. So if you would assume for our sample to be one directional in this, so to test one-sided, then you would assume our sample to be even smarter than, which could be very good. Could be a very good assumption, but that is the thought process that goes into this, right? To determining which choice you make in testing. Okay, so our assumptions. Well, the sample should be it should be a normal sample distribution, which is mostly the case when your sample size exceeds 30. And your measurements should be at interval or ratio level, which sounds complicated, but if you look at the other two options, either being just a nominal value, then something that is just a label doesn't contain any value of size. So only these two, the interval or the ratio value, actually imply an increased size in the actual measurement. So these are two of the assumptions that would hold. And one that I didn't put in here, but which is very important, I'll add it later, is that it should be really a random sample. Because if there's any skewed selection on the sample, then the assumption you would violate assumption of a norm of a random sample from your population, and this could have serious impact on if your null actually holds, because if it's not a random sample, if it's a deliberate sample, then there's actually no way why your null distribution should be true. Now we apply this, so we calculated the t-value based on the actual mean that we found, the assumption of our population mean, and we divide it by the standard error, and I've done that here. So it's a 122.33 minus the population mean that we expect, and we divide this by the standard deviation divided by the square root of the sample size. This is last year that we're doing here. So the thing that I want you to be able to do also in your exam is to be able to calculate these test statistics. So the test statistic for the t-value, well, you can see here, and you have to do the transformation, and we'll be practicing this in the weekly assignments. You have to translate this to some R code. So what you see here is actually applying the formula that you find here. So we're saying the t-value is the mean of x minus mu divided by the standard deviation of x and divided by the square root of n, the sample size. So you have to realize that you have to calculate the mean, you have to calculate the standard deviation, and you have to calculate n still here. And if you do this, you find a t-value of 2.1. So based on what we've been looking at so far, do you think that this t-value of 2.1 is significant or not? Who thinks it's significant? Who thinks it's not significant?
Yeah.
You don't? Who doesn't know?
But is it one-sided or two-sided that we're assuming?
I haven't made a choice yet, but if you just look at this value, would you think it's significant or not? Even disregarding the one or two-sidedness.
No.
I hear no. Is there anyone who says yes?
What is our sample size?
What is our sample size? Our sample size is 50, because we have the 49. It's the square root of n. So our sample size is 49. Who doesn't know?
So I'm still not sure if I can completely understand, but I'd say that it would be significant because it's smaller than 2.5.
Yeah. Could be. Why is this a hard question?
Because we don't have the 48 degrees of freedom t distribution in our mind, and we're not sure where the critical value is, depending on if it's one-sided or two-sided.
That's a very good observation. So you what you're saying is you don't have the t distribution in mind. So what does it look like? Well, we just looked at a large variety of t distributions, ranging from sample sizes 5 to having a sample size of 100, and we always saw that we had a mean of 0, 1, 2, 3, and 4, but that was about the range that we had. And the reason why this is a hard question is because 2.5, well, it's on the brink. It could be. It would be a simple question if the t-value would be 1. Then you could imagine that, well, disregarding the kind of the t distribution that we have, 1 is not rare. It happens a lot. So because this one is so close to the region where a critical value of an alpha of 5% could be, it's hard to answer this question. Makes sense, right? Okay, so if we would assume a type 1 error of 5%, then we would have to determine what the p-value would be. And for now, I'm looking at the p-value one-sided. I will also do the two-sided just to calculate this for you. And what we're doing in this course in R is using the function visualize, because what you've been taught in previous years is to use a lookup table to determine what the p-value is for a specific value of the test statistic. And I don't find this really informative, because it doesn't show you the relation between the actual distribution and the area that you are actually looking at. So we're using this visualize function to, based on this specific t-distribution, based on the sample size, what does the what does the null distribution look like? And based on our found test statistic of 2.1, what is the probability of finding this test statistic or more extreme under this null curve? And what we need for that is the degrees of freedoms, which for the one sample t-test is n-1. And if we use the visualize function, then we can use the visualize t function to put in your t-value that you found, put in the degrees of freedom, and set your selection. So using upper, it means that our one-sided assumption would be that it should be that it was higher. You can also do lower. And what it looks like is this. So we here see what our null distribution of the t-value would be.
I'm sorry, I can't see your slide.
Oh, sorry. Good that you say this.
No, I can.
I'll go back to this one. So we determine we're using the visualize function, this one, and we're putting in the t-value and the degrees of freedom, and we're setting the section to be upper. So we're looking at one-sided at the upper side, and this is what it looks like. You see the t-distribution for 48 degrees of freedom, and what we also see here is that a t-value or more t-value of equal or higher than 2.11 blah, the probability of that is 0.0196, and that probability, just as we discussed earlier, the probability relates to an area under the curve. So 2.1 is here, 2.1 here is our found test statistics. So the answer to our question, what is the probability of finding such a test statistic or more extreme? And we're talking about probability again. That's the area under this curve, under the null curve. And that probability is lower than 5%, as we see. So we determine to refute the null hypothesis. Agree? What aren't we seeing in this null distribution? What are we not seeing?
The critical value for t.
Exactly. We're not seeing the critical value. We're also not seeing our alpha level. And in actuality, when you do research, you don't need these graphs, because you just know if it's lower than 5%, and our alpha is 5%, and I find it a test statistic, a t-value with a probability lower than that 5%, I already know enough. So this function, this visualize function shows you the p-value and the probability of that p-value or more extreme, but it doesn't show you our alpha and our critical value.
I'm sorry, can I ask, what is the difference between alpha and the critical value?
Is there anyone who'd like to have a try in answering this one? Go ahead.
Alpha and the critical value.
What is the difference
between? Right?
So what is the difference between alpha and the critical value? And someone is saying alpha and the critical value is the same.
I think that alpha is just the 5%, and the critical value is the point of the statistic that is kind of the border. And if you have values that are more extreme.
Exactly.
Yeah.
That's absolutely correct. So let's look at this graph. If I would draw a line from this 0 going up to the top, my critical value would be 0. It's just the position on the x-axis. And what is the probability of finding a value of 0 or more extreme if we, for example, go to the right? What is that probability?
50%.
50%. Everybody agrees?
Yeah.
Yeah? So now I'm going to the right, and our percentages, so the 50%, it's the area under the curve. It's the area on the half of the curve. So if I go to the right, this percentages drops. It gets lower, it gets lower, it gets lower. And if I want to determine what 5% is, then I have to determine what is the area under the curve that is 5%. And related to that area is some critical value. If this would be my critical value, then, well, this area is probably more than 5%. So I had to be more to the right. So maybe it's here, because this critical value is associated with 1%. So it's probably here somewhere. So the difference between the critical value and the p-value, the p-value is the probability, which is an area under the curve, and the critical value is the associated value on the x-axis, where the exactly as was pointed out, where the border is for that area.
Okay,
does that make sense?
Yeah, thank you very much.
Very good, you're welcome. So the p-value two-sided, and this is a strange thing, right? And I'll stop after this. But if you do two-sided, because your alpha is 2.5% on one side and 2.5% on the other side, you actually have your, because you just calculate just one t-value, it's 2.1. But if you test two-sided, you put one on the left side and on the right side. So if I have a p-value here, and I test two-sided, and it's also on the left and on the right, my actual p-value that I have, so the area of the found test statistic, 2.5 or minus 2.5, or more extreme, to the left or to the right, is, because it's two sides, it's double that area. Agree? And now we have a bit of a problem, because sometimes, no, most of the times, SPSS reports the p-value for two-sided testing. So if SPSS does a t-test for you, it says it gives you a significance level, and that is two-sided. And if you decide to have a one-sided test, you divide your p-value by 2, because one side just drops out. I've made a short knowledge clip on this, which is also on the lecture page, so make sure to watch that to get a more intuitive notion on this. But it's good to realize that for these, and that's an important point, for these symmetric probability distributions, you have you can test one or two-sided, but SPSS always gives you the results of the p-values two-sided for these symmetric tests. So if you have a specific direction of your hypothesis, you can divide the p-value in SPSS in the results by 2. Okay. The effect size we can calculate, and I will leave it at that. That was a long one again, huh? We'll go into this in the weekly assignments. Next lecture we're also going into the t-test, but then the independent and the paired sample t-test. So we'll be diving in here much more. Thanks for your time. I'll be sticking around for some questions if there are any, and hope to see you next time. Bye everyone.
Bye bye.
Bye.
Bye. Bye.
Bye.